Okay, so the plan for today is to go through another application of integration, and this one is probability. So a little more abstract than the previous one, moments and centers of mass. But I think we'll see some relationships between the two actually. And one of the reasons that I picked this out as one of the applications that we do cover, I don't think a lot of folks cover it in Calc 2, but it's in our textbook, so it's, uh, there is a treatment in the textbook, and most folks who are going into or who are taking Calc 2 are going into fields where you'll need something like an engineering stats course, maybe a probability course. So if you're going into something engineering related, engineering stats, if you're going into maybe applied math, like a course in probability theory, um, yes, so you're going to see this material come up again. Um, so uh, so I think that it's worthwhile to have a bit of an introduction to it. But that being said, this like I kind of suggested is a field that can be a lot bigger than just one lecture. So moments and centers of mass. I mean, we covered pretty much what there is to say about it in our previous lecture. But probability, you can take an entire course on probability theory. Well, you can take a lot more than that, but just, kind of the standard calc-based probability. Um, yeah, just the standard calc-based probability theory can be an entire, one semester course, perhaps even 2 semesters, depending on if you go a little bit deeper into it or something. And actually, I set up an experimental course on probability theory several years back. Ended up not really actually being able to run it. We just couldn't get the days and times quite worked out. But um, so this is a topic that most of you will see come up later on in your academic careers, and having a little bit of an introduction to it, I think really just smooths it over whenever you see it in an actual course later on. Um, in actuarial science, we use this kind of stuff all the time, so that was my exposure to it. And the quote of the day, kind of related to us talking about probability today, is George Box, the statistician's quote that all models are wrong. That is a typo. All models are wrong, but some are useful. And so it's important to remember that when we're talking about these probability models, at the end of the day, these are models. So we might be modeling something in the real world with something that's a mathematical model, and it's quite likely that that mathematical model doesn't fit the real world characteristics perfectly. But the question is, does it fit well enough that it is useful? And hopefully the answer is yes. Okay, so we've got a lot to get through. I don't know how far we'll get in class and how much I'll kind of punt to a supplement, but we'll just kind of start working through it. So to start off the discussion, we'll discuss the discrete case with equally likely outcomes, and then we'll move pretty quickly into the continuous case, which is where we'll spend most of the lecture. So I can talk for for quite a while about this stuff, so I'm going to really try to keep my kind of side comments and ancillary material pretty brief here. And so we're not going to talk too much uh, about things like randomness and probability and what they might mean in some philosophical sense or in some applied sense. But we're going to start off by just saying, let X be a random variable. What is a random variable? At this point, we're just thinking of it as some kind of mathematical structure. Um, so at this point, we're not thinking of it as having really an application to the real world. Now, a little side note, because that's not a super helpful thing to say, we just, you know, give some abstract entity a name. Um, when we think of a random variable, we think of something like, say, for instance, a die roll. I roll a die, like single of a pair of dice. In the discrete case, I get 1, 2, 3, 4, 5, 6. It's discrete because I can look at a potential outcome, say the number 2, and I can ask, what's the next biggest one? That would be 3. Or from 3, what's the next biggest one? 4. That's what makes it discrete. Whereas if I was, say, measuring the height of something, um, well, if I say this one measures 5 feet long, what's the next allowable height? Well, it's not really 5 feet 1 inches. There could be something, there could be a height between those two, or it's not really 5 feet and 0.1 inches. There could be a height between those two. That's a continuous uh, variable. So uh, I'm being a little bit hand wavy on this stuff. That's not exactly a precise um, argument, but again, I'm trying to keep my pedantry to a minimum here. So that's what we mean when we say a random variable. It's an experiment that we're going to run, or we imagine running, and we don't know what the outcome is going to be. So instead of trying to predict the outcome using something like physics, uh, we look at all possible outcomes and we try to say something about the characteristic of maybe all possible outcomes. That's kind of our goal here. In this mathematical model, the sample space is the set of all possible outcomes of X, of the random variable. So in our die roll, the sample space would be the set 1, 2, 3, 4, 5, 6. Or if we were flipping a coin, the sample space would be the set heads, comma, tails. For our purposes, we are assuming that all outcomes are equally likely. So like a die roll, 1 through 6 comes up equally likely, coin flip, heads and tails equally likely. We, of course, as you can imagine, can certainly generalize this. But again, that's kind of outside the scope of what we're going to discuss today. But this certainly could be generalized. But for our purposes, we're assuming equal likelihood of all outcomes. So we have a sample space of all possible outcomes and an event E. So when we talk about an event, that's a subset of outcomes. So an event could be something like rolling a die and getting an even number. So the outcomes 2, 4, 6 would be members of the set that we're calling the event E, while 1, 2, 3, 4, 5, 6 would be the sample space. E, a subset, could be a couple of the outcomes from the sample space. It could be most of the outcomes from the sample space. It could even be all the outcomes from the sample space. I roll a die and my event is getting a number less than 10. Well, of course, 1, 2, 3, 4, 5, 6, all members of the sample space happen to qualify for that event. My event could even be the empty set. If I roll a standard 6-sided die and my event is getting a number bigger than 10, of course, there are no outcomes in the sample set, 1, 2, 3, 4, 5, 6, or sample space, 1, 2, 3, 4, 5, 6, that satisfy that that number is bigger than 10. Okay, so X is a random variable, just kind of an abstract entity at this point. The sample space is the set of all possible outcomes of X, and an event E is a subset of those outcomes. And as I mentioned, we're assuming for our purposes, all outcomes are equally likely. So definition, the probability of an event E is the ratio of the number of outcomes in E to the number of outcomes in the sample space. The probability of the event occurring is the number of outcomes in the event over the number of outcomes in the sample space. If we're talking about our die roll example, what's the probability of rolling an even number? Well, 2, 4, 6, I have 3 outcomes in the event, and 1, 2, 3, 4, 5, 6, I have 6 outcomes in the sample space. 3 over 6 is 1/2, 50% chance of rolling an even number on a fair 6-sided die. Again, this is all under the assumption of equal likelihood of outcomes. Things get a little more complex if we admit the possibility of outcomes that are not equally likely. So super important caveat here for just everyday life. There are people who will say, oh, well, you know, there's such a thing that I'm interested in, and there are 2 possibilities, so it's a 50-50 shot. Well, that's not necessarily true. I mean, we can think of absurd examples that demonstrate the falsity of that, right? I play the Powerball. There's 2 possibilities. I win the Powerball jackpot and become a billionaire or whatever, or I don't win the Powerball jackpot. There's 2 possibilities, a 50-50 likelihood, right? Well, no, of course not. Because in the Powerball, well, winning the Powerball is much, much, much less likely than not winning the Powerball jackpot. So we don't want to, all models are wrong, but we don't want to apply a model in a situation where it's so wrong that it's completely useless or even the opposite, even misleading. So be a little bit careful with that. You know, we're typically thinking of situations in the simplest case that we've devised, things like die rolls, things like rolls of a roulette wheel, things like coin flips, right? You know, there are some things in nature that are equally likely, things like male versus female births, about equally likely, more or less. Um, but, you know, not too much in nature, or not too much that kind of naturally occurs, is equally likely. So we are talking about a model with a pretty narrow scope when applied to reality here. But again, we're not looking to exhaust our discussion of the discrete case here. That's far too much for even one lecture just to talk about the discrete case, let alone move into the continuous. Couple of notes. Note that the probability of an event is always between 0 and 1 inclusive for any event E. If event E is a subset of the sample space, the set of all possible outcomes, the event E can have at most the same number of outcomes as the sample space. The biggest my numerator can be is the same size as the denominator, and that would be a ratio of 1. And the smallest my event E can be, the least the number of outcomes I can have in my subset is 0. I can't have like negative number of outcomes in my subset. If I have an empty set and there's nothing in it, that's as small as that set can get. That would give, of course, a probability of 0. One minor note here is we can have discrete random variables that are kind of infinite in some sense. So we might have a random variable like the number of coin flips until you get a head. So if you flip tails, 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 heads, that would be 3 because you got 3 tails before you got a head. That's discrete in the sense that if I have one outcome that is 3 tails before a head, what's the next possible outcome? 4 tails before a head. It's discrete in that sense, but it's unbounded above. So there's a little bit of nuance here with what happens to this probability ratio when my sample space is infinite in that case, but we're going to kind of ignore that. Again, we're not trying to put together an exhaustive discussion of probability here or a super formal definition for probability. We are just looking for an expository lecture here. So, and we have not a ton of time to get through it. Okay, and our second note here is that if the probability of an event is 0, and again, these are both under the assumption that we have a non-infinite sample space. If the probability of an event is 0, exactly 0, the number of outcomes in the event must be 0. The event E is then impossible. There are no outcomes in this random variable. There are no potential rolls of a die, for instance, that result in our event being true. So we say this event is impossible. And likewise, if the probability of the event is exactly 1, not just, you know, kind of close to 1 or rounds to 1, but if it's exactly 1, then we say the event is certain to occur because the event must contain exactly the same outcomes as the sample space, which is all possible outcomes. So whatever outcome we get is going to be in the sample space, but also in the event. That is a certainty. That means that the event is certain to occur. Okay, so that is a little bit of just kind of the nomenclature and so on, thinking through the discrete case. We're going to jump into the continuous case now, where we're thinking of x being a continuous random variable. And let me just write that explicitly. Let x be a continuous random variable. So what are we thinking about a continuous random variable? Kind of roughly speaking, what we're thinking about is if I'm looking at any particular outcome, and if I ask the question, what's the next possible outcome? That question doesn't really have a good answer. If I'm rolling a die, if I say, okay, one possible outcome is getting a 3, what's the next possible outcome? A 4. What's the next one after that? A 5. I can take discrete jumps between my outcomes. But again, if I'm measuring height or width or weight or speed or these kind of things, time, something like that, those are going to be more continuous random variables, at least for most applications. Um, right? We're going to ask, okay, how long did this thing take? Okay, it took, whatever, 35 minutes. Well, it's not like it took exactly 35 minutes. It's not like 36 minutes is the next possible amount of time. It could take 35 and a half minutes or 35.1 or 35.003 minutes. Another way to think about a continuous random variable is that effectively these have to be rounded. And that if I had a more accurate measuring device, I could get more decimal places of accuracy when I measure my outcome. That's another way to kind of think of it. The continuous random variables, when I write out the uh, the measurement, it has to be rounded because otherwise it would just be a string of decimals that goes on forever. Where if I roll a die, a three is a three. It's not like it's not like 3.0001, which is about three. It's like, no, it's exactly a three. Or if I count, number of students enrolled in a class, it's three students or four students. It's not like about three students or about four students. If I got a really accurate measuring device, it would still be exactly three students in the class or still be exactly a die roll of four. Where a continuous random variable, the more accurately I measure it, the more decimal places of accuracy I'm able to obtain. So often thinking of things like physical quantities. Okay, so some definitions. We have a bit of a bit of an issue here. When I was in my discrete case, I could just kind of count up number of outcomes, right? I could just count the number of outcomes in the event, number in the sample space, divide them, and that gave me a notion of probability. With a continuous random variable, if I'm interested in, what's the probability that somebody is between 5 feet 10 inches tall and 6 feet tall, I can't just like count up all of my different possible outcomes there because there's no sense of next one, right? There's kind of in between any two potential outcomes, there's infinitely many outcomes. So I almost have like an infinity over infinity type situation popping up here. That's an indeterminate form. How do I resolve that? Well, the answer is I use something called a PDF, a probability density function. So this is fairly abstract. If we were going to go through more detail, we would take the discrete case, kind of draw out a picture for what this might look like, talk about the continuous case being a limiting case of the discrete case, and so on. So there's much more that goes on behind the scenes here, as I've alluded to a couple of times already. But we're not going to go into all of that. But you can think of the continuous case being kind of a limiting being like a limit of the discrete case, an idea that we've seen before several times in Calc 2. Okay, so we have a function, a PDF, a probability density function, that we use to describe the distribution of the random variable x. Now note the notation here. We have little f subscript big X of little x. And I want to note what each of these things is doing. This is kind of a funny way to write this. There seems like there's a lot of extra stuff here, particularly this little subscript x. The little f, that is the thing, that's kind of the trademarked letter for a PDF in stats. So if I see little f as my function, I think it's a PDF, probability density function. I have a little bit of a problem though. I might be looking at the PDF evaluated at an input of 3. So here little x is my input. This is a function, so I want to be able to put in inputs. But what if I have two random variables? What if I'm measuring heights, but I have the heights of men and the heights of women? I have two different variables, two different PDFs that I'm going to be interested in. But in both cases, they've got to be called little f because little f is the trademarked name for a PDF. How do I distinguish between the two? Well, maybe I name the men X and the women Y. I, actually, probably I should do that backwards, but men Y and women X, I guess. But how do I distinguish between the PDF that goes with this random variable versus the PDF that goes with that random variable? That is where the subscript comes in. The subscript big X represents our random variable. So that if I have more than one PDF floating around, I can talk about this one versus that one. It's going to be little f everywhere because little f is the name for a PDF. If I want to reference the PDF, I use little f. And then the way that I say this distribution or that distribution is with the subscript denoting the distribution. Right. The input isn't sufficient using little x or little y or something because, I'll be looking at, say, little f of x, little fx of, say, 3 or something like that. Well, if I just had little f of 3, uh, I don't know what random variable that is, right? The name of my input variable has gone away when I input a number. So that's the reason this notation looks a little funny. I don't think your book uses the subscript notation, but I think it actually is important because otherwise, how are you going to tell different PDFs apart? We don't want to call them different names. We don't want to call them like little f, little g, little h. That's not really the way that the notation is commonly done in stats. Okay. So the PDF is denoted little fx of x, or little f sub x of x, something like that. And we have some criteria for a function to be a PDF. You can define PDFs in kind of slightly different ways, slightly basically analogous ways. But if you define it a different way, then it makes some of these definitions down here kind of annoying to deal with, like that one, or uh, like this one. So some of these definitions, then you have to say, yeah, except in this case or something like that. Um, so we're going to say a function is a PDF if the following are true. One, it's defined for all x in R on the real line. Now, it can be 0 in a bunch of the real line. That's perfectly fine, but it has to be defined everywhere. Two, it has to be bigger than or equal to 0 on the real line. This is analogous to this piece up here. The probabilities, which are going to be related to PDFs, have to be non-negative for it to be kind of sensible to talk about a probability. In the discrete case, that has to be true. This is kind of the equivalent form of that in the continuous case. And third, kind of this side of things, probability of E has to be less than or equal to 1, or if an event is certain, then its probability has to be 1. When we integrate the PDF over the whole real line, we have to get 1. Integrating the PDF over the whole real line is kind of like saying, okay, I have a random variable that is modeling people's heights. What's the probability that somebody's height is between minus infinity and plus infinity? Of course, it's got to be 100%. We've covered the entire spectrum of possibilities from minus infinity to plus infinity. That has to be 1. If our function satisfies these 3 criteria, then we call it a PDF. Now, some folks omit this first requirement, and they say it's just got to be bigger than or equal to 0 on its domain. But then you have to say, okay, then the integral over the whole domain has to be 1. And it's kind of annoying to write integral over a domain and not have it look goofy. So I think it's easier to require it be defined for all x and r and just let it be 0 on any region that you don't really want to deal with it. Okay. So we have an idea of what probability is in the discrete case. How does that move over to the continuous case? Probability is number of outcomes in the event over number in the sample space. Well, here we define the probability of an event E. Here my event E is the set of all x's that are in the interval AB. So that's what I'm considering an event E here. In the continuous case, my events usually look like intervals. So I might be asking, what's the probability that somebody's between 5'10" and 6 foot tall? How do I compute the probability of an event? I integrate the PDF between the endpoints of that interval. Now, a theorem, the probability x equals a for a continuous random variable is 0. Why is that? It's because this probability will be integral from a to a, fx of x dx, which is, of course, 0. We're integrating over a region of 0 width. Our lower and upper bounds of the integral are the same, so this integral is 0. So in a continuous random variable, get rid of these. There we go. So in a continuous random variable, the probability the random variable equals any specific number is 0. That kind of makes sense because, if you say that somebody's about 5 feet 10 inches tall, kind of after a couple of decimal points, it's almost like you can kind of imagine it being like for each successive decimal place, we're almost like rolling a 10-sided die to decide whether that next place is going to be 0 through 9. So if they're, 5 feet and 10.03 inches, well, 0 3 what? It's almost like a roll of the die for what the next digit's going to be and the next one and the next one. If I was to say what's the probability somebody is exactly 5 feet and 10.03 inches, then every one of those infinitely many die rolls that could come up anywhere 0 through 9 would all have to be zeros. And I think we can see that the more times that I require that the next one be a 0, the less likely it's going to be for that to occur. If I say you need to roll 4 zeros in a row on a 10-sided die, that's going to be unlikely. If I say you need to roll 400, that's going to be essentially impossible, and 4,000 is probably not going to happen in the history of the universe or something like that, right? So in a continuous random variable, the probability that x equals a specific number is 0. It's not like incorrect to ask what's the probability that somebody is exactly 6 feet tall. It's just kind of a boring question to ask because it's always 0. So that's why our events, we typically have events that are intervals. What's the probability somebody's between 5'10" and 6 feet tall? Well, if they're about 5 feet and 10.03 inches, plus or minus, a thousandth of an inch or so, or a couple of thousandths of an inch, well, we know for sure they're between 5'10" and 6 feet. We can get more decimal places of accuracy if we wanted to, but that's not going to change the fact that they're between 5'10" and 6 feet tall. So when we're talking about events in the continuous world, we're talking about events that are interesting and non-trivial. We're talking about intervals. Okay, so another definition, the cumulative distribution function, the CDF, big Fx of x, is defined as follows. Just a quick aside on notation, big F x of x. The big F signals that this is a CDF, a cumulative distribution function. Big F versus little f tells us what kind of function it is, what kind of model for this random variable it is. Is it the PDF or is it the CDF? Is it little f or big F? Little x is the input. And again, if I have more than one random variable floating around, I use a subscript to denote the name of the random variable that it's describing. So the CDF, the cumulative distribution function, big F x of x, it is the probability that the random variable big X is less than the input little x. Or in other words, it is the integral from minus infinity to x, right? What was the probability here? The probability of a random variable is less than x means the probability of a random variable is in the interval minus infinity to little x. So just matching up bits with our probability definition. That's integral minus infinity to little x of the PDF. So the CDF, the cumulative distribution function, it's cumulative because it's accumulating probability starting at the left at minus infinity and working its way all the way up to whatever the upper bound is that you're giving, little x. The CDF is, oops, didn't quite get that arrow in the right place. There we go. Is the integral of the PDF from minus infinity to little x. And a theorem by fundamental theorem of calculus, provided things are nice and continuous and differentiable and so on, the derivative of the CDF is the PDF, right? Big F is integral minus infinity to little x of little f. If I differentiate both with respect to x, with respect to the upper bound, I use fundamental theorem of calculus part 1, and the derivative of the CDF is the PDF. One little aside, you might notice in the integrand here, little fx of t dt. Why did I use a t here instead of a little x? Well, it's because the variable of integration is just the dummy variable. I wouldn't want to use little x inside of the integral because little x already has, it already is representing something. It's representing the input to the CDF, which places it in the upper bound of our integral. So I don't want to use little x in the inside of the integral, which would be using the same notation for a different meaning. And then it would likely get confused. So here I just use a different dummy variable of integration, t, inside the integral because little x is already kind of taken up as the input to the CDF in the upper bound of the integral. Okay, so I want to give a short aside on the meanings of some of these words. I'm going to set myself a strict time limit of 5 minutes here so that I don't ramble on too long. So each of these words we've used a decent bit, and I want to talk just a little bit about them. So maybe a minute or so on each of them. Again, this is meant to be an expository lecture. We're talking about some ideas here. We're laying out some definitions. And in a minute here, we are going to go through some examples, do some calculations, see how integrals are used. But this is not meant to be, you know, or to be the equivalent of something that might be like a month or so of lectures in a probability theory course. Okay, so what is randomness? From our perspective, randomness is a mathematical model. So we have something like the roll of a die. You say, okay, well, if we understood Newtonian mechanics well enough, and if we had a big enough supercomputer, and if we had sensitive enough sensors that could look at the way that the die is moving as soon as it leaves your hand and can predict how that die is going to interact with all the surfaces it's going to bounce against and all of that quite well, then I think we would agree that when the die leaves your hand, this fancy computer could say, okay, it's going to come up a six, and it comes up a six, or it's going to come up a one, it comes up a one. It could predict it with a very high degree of accuracy, at least in theory. But the thing is that we'd have to have such incredibly sensitive sensors and such incredibly detailed models for that when the die hits this piece of carpet, does it hit at the corner or an edge or a face? It would be extraordinarily difficult. At the very least, it would be infeasible to have that calculation completed by the time that the die comes up, whatever number it comes up. Uh, so we're thinking of this as a mathematical model. We're saying, okay, maybe in theory I could predict this with physics, but it's so complicated. It's really a chaotic system, is what it is. And what that means is that a small change to the input can cause a large change in the output. So if I throw the die at just a little bit of a different torque on it, or a little bit of a different speed, or from a little bit of a different height, I move the height 1 millimeter, and all of a sudden a one, the lowest value, can go all the way to a six, the highest value. A tiny change in any input can cause a massive change in the output. So I can't get, so I would need a very, very, very accurate uh, knowledge about the inputs and how they propagate through the system to really be good at predicting the outcome. That's infeasible, maybe impossible. Um, and at the very least, I don't really want to do that. So I set up a mathematical model that I call random. And I say, okay, we're going to presume this is a random process that when you throw the die, like nothing in the universe could possibly predict what it is. It's going to come up 1 through 6 equally likely. And we have no idea what it's going to be beforehand. So I think there is an idea in physics called like Langevin dynamics. There's a lot of different ideas where they basically just say all of these really complicated terms, we're just going to kind of make them a random term and let that encapsulate the effect of that. So it's a mathematical model. Philosophically, things like quantum mechanics might bring that into question. Is randomness actually underlying the nature of our reality? That's a question that is beyond the scope of probability to answer. It's a mathematical model. Its application will be fallible. All right. I might say that, well, I think heights are maybe approximately normally distributed. We'll see what that means in a couple minutes here. And you might come back and say, wait, so you're saying that there is some positive probability that a person is between negative 20 feet tall and negative 30 feet tall. Yeah, that's what the model says. But that probability is so extraordinarily small. All models are wrong. Some models are useful. We're probably happy using this model because the probability that somebody's negative feet tall or, more than 40 feet tall is like 10 to the minus 1,000 or something. And that's effectively zero for our purposes. So the application of the model to reality will be fallible. There will be some caveats and things, but hopefully it will be useful. That's our goal here. Probability. What is probability? It's the chance that something occurs. Roughly speaking, let's take something like the weather. There's a 20% chance of rain tomorrow. What does that mean? That means if I take 100 similar days to today and I look at the next day and ask, did it rain or not? On 20 of those days, it will have rained, and on 80, it will not have rained. So I say, okay, today it looks similar to these other 100 days. On 20 of them, it rained the next day, and 80, it didn't. So we'll say there's a 20% chance of rain today. That's essentially what we mean by probability. Again, there are different aspects of probability. There's the whole Bayesian structure where probability represents the degree of belief. But this is, I think, a good first pass of what probability is. On lots of equal or lots of similar runs of the experiment, this is the proportion of times we think we'll be in the event versus not in the event. And interpretation of PDF, let's actually just stop with that one. And if I have a PDF, a function like this, it is a density. It represents probability density. not probability itself. It's a linear density, so I need to accumulate across one dimension to achieve a mass, to achieve an amount. Just like with any normal density, right? If I have a substance, if I have a rod that's whatever, um, 1 pound per linear foot, I have to accumulate a certain amount of that rod, cut off a half of a foot, and it's a half of a pound or whatever it is. I have to accumulate a density across its distance, its area, its volume, whatever kind of density it is, to achieve an amount. A probability density I have to accumulate across a linear distance to achieve a probability. This area represents that probability. Accumulating across a linear distance, the linear probability density gives me an amount of probability. So if this is a PDF, why do I integrate it to get probability? It's because it's representing a density, and I need to accumulate a density, a linear density in this case, over a linear distance to achieve an amount, in this case of probability. I have a linear density of probability, given my little f. I accumulate that across a linear distance, and that gives me an amount of probability. So that's why it's sensible for this to be the definition. And that's why we call this the probability density function. That's what it represents. So importantly, something like little f of 3, this number here, this height of the function at this point, doesn't really mean very much. It kind of does a little bit, but it doesn't really mean very much. What really means something interesting is the accumulated area between two numbers on the real line over some interval on the real line. And this is why we are more interested in the continuous world. We're more interested in talking about events uh, that are intervals, because we get to accumulate probability density over an interval, and now we really have some probability to talk about. If I have a probability density, if I tell you this bar weighs, 1 pound per foot, per linear foot, and you have none of that bar, how much weight do you have? None. I don't care if that bar weighs 10 pounds per linear foot or 1,000,000 pounds per linear foot. If you have 0 feet of the bar, you have 0 weight. If you have 0 linear distance that you've gone to accumulate probability from the probability density, I don't care how big the density is, you have 0 probability. You haven't accumulated anything over the linear distance. That's why the probability is 0. Okay. All right, well, I've already surpassed my 5-minute limit by quite a bit, but I think we will leave that there. We have a few canonical distributions. In theory, any function that satisfies these 3 criteria is a PDF. But the problem is, if I come up with some goofy function, little fx, what's the chance I'm able to integrate it nicely to get a probability? Or what's the chance I'm able to get a nice looking CDF out of it? Well, there are some functions that work pretty nicely. They work nicely mathematically. They have some nice statistical properties. So for instance, if I know that I have a continuous random variable that's bounded between two numbers, there's a sense in which the most sensible distribution to use is the uniform distribution in some statistical sense, in this maximal entropy sense. So they have some nice statistical properties for these distributions, some nice mathematical properties. We can do the integrals and come up with formulas, and they have nice properties uh, in that, for instance, I can evaluate the CDF, and it's going to be, at least for most of these, a closed form expression. Or I can, even coming down here, talking about the expected value, I can find the expected value or the mean of these distributions, and it's going to be a pretty nice a pretty nice function of the parameters of the distribution. So these are distributions that have interesting statistical properties and that work nice mathematically. These are not by any stretch of the imagination the only PDFs allowable, but these are a selection of 4 that have interesting stats properties and where the math works pretty nicely. So they're also pretty commonly used. They fit a bunch of applications pretty nicely, so they're in popular use as well. The first is the uniform distribution. Our PDF is bounded, well, its non-negativeness is bounded on alpha to beta. So it is height 1 over beta minus alpha on the interval alpha to beta, and it's 0 everywhere else. So 0 here and there. So a lot of times our functions, our PDFs are written piecewise like this because we want to make sure it's defined on the whole real line. So we just set it to be 0 anywhere that we're not interested in. Here we're interested in just the interval alpha to beta, and so everywhere else we set it to be 0. So if I only know that my distribution is bounded on alpha to beta, this is probably a good distribution to use. It satisfies a nice statistical property. My exponential distribution. This is defined on the positive real line. And it looks like an exponential decay to 0. And on the negative real line, it just is 0 everywhere. So we say that y, if y is an exponential distribution with parameter lambda, lambda is the parameter that's often used for the exponential distribution. We would say that its PDF, denoted by little f, subscript big Y of little y, is when y is bigger than or equal to 0, it's lambda e to the negative lambda y, and 0 otherwise. So this is little f subscript y. Now you see why we're using the subscript so that I can discriminate between the different distributions. Otherwise, we'd be calling both of these little f, and we wouldn't want to call the second one little g because that's not really the nomenclature for a PDF. The standard normal distribution, the so-called bell curve, centered at 0, and it looks more or less like this. These inflection points are at 1 and -1. This is actually defined on the whole real line. We often model things like heights or maybe weights or IQs, things like that, with a bell curve with a standard normal distribution. And we accept the fact that sometimes the model is going to give us a silly statement that there's some probability that you have a negative height. But this tails off to 0 so quickly. It's e to the minus z squared. That goes to 0 very, very quickly. That what's the probability of somebody having a negative height under the model? It's so close to 0, you might as well call it 0. So is that a practical issue with the model? Not really. It's more of a pedantic issue. And we're usually happy to just ignore those little inconsistencies in favor of using a nicer model like this one. If I were to say chop this off, I was saying 0, 0 is there, but that would be more related to the general normal. But if I were to chop this off somewhere down here at like -3 or something, that would introduce like a discontinuity. That would introduce this function would be really hard to integrate and to figure out, this 1 over root 2 pi is there as a correction factor to make sure that the whole area under the curve is 1. It's going to make all of this so much more complicated. I would rather just stick with the simpler model that does, practically speaking, just as good of a job. And the general normal distribution, so this is what we would use to model something like heights or weights or something like that. It's centered at a position denoted mu, this Greek letter mu, its parameter that is up here, and its inflection points are mu plus sigma and mu minus sigma. Its other parameter sigma, Greek lowercase s, we see popping out there. So it's basically like our standard normal distribution that's shifted from 0 to mu and either maybe stretched out or compressed horizontally so that the width between the inflection points is 2 times sigma instead of simply 2 units. So mu is the location parameter. It tells you where it is left to right, where it's located. And sigma is kind of a shape parameter that tells you whether it's like wide and squat, like wide and short, or skinny and tall. Okay, so let's take a look at this example. I will leave the uniform distribution as an exercise. And we'll talk about the exponential distribution. So let's look at the random variable y, which is exponential with rate or with parameter lambda. Let's copy this down. And let's show this is indeed a PDF. Is fy bigger than or equal to 0? Well, for the negative inputs, it's 0. That satisfies bigger than or equal to 0. For the positive inputs, it's lambda times an exponential function. The exponential function is positive. And by assumption, our parameter lambda is positive. So yes, criterion 1 is satisfied. So what is criterion 2? I'm sorry, I skipped. Criterion 2 is satisfied. Criterion 1, is it defined on all of R? Yes, it is. I got ahead of myself. And criterion 3 is usually the interesting criterion. So is it true that the integral minus infinity to infinity fy of y dy equals 1? This is the interesting criterion typically. Well, let's check. Well, integral minus infinity to infinity fy, half of that interval is 0. So really, this is just integral 0 to infinity of lambda e to the negative lambda y dy. Or this is lambda. I integrate e to the minus lambda. That gives me an e to the minus lambda y. And I need a 1 over negative lambda. So I have negative lambda over lambda now, evaluating from y as y goes from 0 to infinity. So this gives me negative 1 times, as y goes to infinity, lambda y, remember lambda is positive, also goes to infinity. Negative lambda y goes to negative infinity. So I have something that goes to e to the negative infinity, or 1 over e to the infinity. That goes to 0 minus, evaluate at y equals 0. E to the 0 is 1. Negative 1 times negative 1 is 1. We have shown that the exponential distribution does have total area 1. This total area under this curve is indeed 1. Okay. I was a little hand-wavy with my improper integral here. If I wanted to be really precise, I would put a b here and then limit as b goes to infinity. I kind of did that all in one step. So if you didn't kind of catch how that improper integral was handled in this step, um, go back through, fill in some of those details in your notes. Or if you just want a little more practice with improper integrals. Okay, let's find the CDF, the cumulative distribution function, for each of the uniform and exponential distributions. And again, I'll leave the uniform as an exercise. As an aside, these are all very common distributions. You can look them up on Wikipedia, and if you compute the CDF, you can see if what you computed is the correct CDF. So for the exponential distribution, recall that the CDF is the integral of the PDF from minus infinity to whatever we're calling the variable. So our cumulative distribution function is going to be integral minus infinity to, we'll call it little y here, little f subscript y of t dt. Well, this is really just, this can be split into two cases. One case is y is less than 0. Big F is just 0 then, of course. Integral negative infinity to a negative number, little f is just 0 on that whole interval. But if y is bigger than or equal to 0, this is just integral 0 to y of my PDF. But wait, my PDF when y is bigger or equal to 0 is simply I need a t there, lambda e to the negative lambda t dt. So this is the value of my PDF when y is non-negative. So this is negative lambda over lambda e to the negative lambda t from 0 to y, or negative 1. This is e to the negative lambda y minus e to the 0 is 1, or this is 1 minus e to the negative lambda y. So what is big F then? It is 1 minus e to the negative lambda y bigger than or equal to 0, and lambda bigger than 0, and it is 0 otherwise when y is less than 0. This is my CDF. Okay, so I know that was, let me stop the recording.